There are numerous legends surrounding powerful Japanese swords with incredible strength, such as Ishikiri-maru, which is said to have cut a massive rock in half, and Ishidoro-giri kotetsu, which cut through a stone lantern nearby when cutting a pine branch. Although these stories seem exaggerated, they might have provided interesting insights into how swordsmith's craftsmanship can affect a sword performance. What do you think? The answer is that the sword strength can vary significantly depending on how it is made. In this video, I will discuss scientific possibility of creating the strongest swords by exploring the effects of grain size on steel. In this channel, we share scientific knowledge of samurai culture and exciting facts related to traditional Japanese practice. If you're ready to level up your knowledge of samurai culture, don't forget to smash the subscribe button and join us on the journey. Have you ever wondered how slight changes in the processing of the metals can drastically alter their strength? It's fascinating to consider that even metals with identical appearances can have widely different properties. Take copper for example. This is 99.9% copper bar, and the thickness is around 2 mm, very thin. However, it's really difficult to bend with my bare hand. But once it is heated up to high temperature and cool down, look at this. This becomes incredibly soft. Only 2 fingers is enough to bend. This is an example of how the strength of the metal changed with a simple heat treatment. Of course, not all metal is affected in exact the same way. Aren't you curious about how the heating treatment during swords making affects its strength? Today I will discuss the importance of internal structure within steel for creating strong swords, explaining why it occurs and how it can be achieved. In the final part, I will present a previous study that explores how the internal structure of Japanese swords varied across the different historical eras. Actually, the steel, which is a material of Japanese swords, has a structure looks like a lump sticking together when viewed under a microscope. Each of the lumps is called a crystal grain. This happens because the orientation of the crystals in each grain is different. Atoms have a comfortable positional relationship with each other, making them easy to connect. This leads to the formation of beautiful shapes like crystals. When iron or steel is heated and melted, and then cooled down, various small crystals form and grow independently from each other. This results in a large mass of iron with crystals sticking together in different orientations. It is known that the smaller the grain size in the metal, the higher the various strengths can be. I will explain the principle behind this in 2 parts. The first reason is that the deformation is difficult because the strains and defects within the crystal grains is not easily transmitted. There will always be defects and strains within the crystal grains, and it becomes impossible to have a perfect, beautiful crystal as the size of the crystal grows. When there are defects, the crystal will easily shift and deform in a particular direction. However, when the crystal grains are small, they can more easily act as a stopper for each other. They become harder and less likely to deform under impact. The second reason is that the area of the crystal grain boundaries is large, allowing the absorption and dispersion of the impact at the boundaries. The space between the crystal grains is relatively easy for atoms to move, so when the impact occurs, these atoms can absorb the energy as a whole and prevent the force from being localized. When the crystal grains are small, the area of these grain boundaries becomes larger, making it easier to absorb impact. Now I know you are curious about how much the strength actually changes. There is a useful formula called hole patch equation. The equation estimating the strengths of materials. Based on this, the smaller the grain size, the higher the tensile strength. For example, steel typically has a grain size of 25 micrometers, when well made. But if a several micrometer grain size can be achieved, the strength can be more than double. So various research is being conducted for industrial applications. In extreme cases, using the same material, the sword strength can change by more than double depending on how it's made. I will tell you how we can make a sword with smaller crystal grains. You can imagine crushing ice to make it into small pieces while preventing them from melting and sticking together. If you want to crush them, you need to hit them with a large energy. If not, they just move and size never changes. And you need to keep a low temperature. If the temperature is high, their surface melts a bit and easily stick together, forming larger pieces. I'll explain the case of metals. When copper is heated, its crystal grains combine together and form larger crystals, making it much softer. As the metal is heated, the atoms begin to move more vigorously, and atoms at the boundaries between crystal grains, which are not tightly fixed, gradually merged and form the same crystal. As a result, larger crystals are formed. The higher the temperature, the more likely the crystals are to grow larger. To avoid larger crystal formation, it is necessary to create the materials at relatively low temperature in a short time. This is below around 700 degrees Celsius, the temperature at which iron berry turns red. If a blade is made at this temperature, it is difficult for crystal grains to grow. Moreover, to make the crystal grains even smaller, a large amount of energy must be applied in a short time, enough to crush large crystals. Instead of using a flat hammer, I think it's more effective to use the rounded one to strike the material, so that the deformation is as large as possible. It is common to distinguish between swords made before and after Edo period, referring to the former as koto and the latter as Shinto. People often claim that koto possesses superior sharpness, color, and a distinct sensation during sharpening. But I find it interesting to speculate on how changes in heating techniques and forging process throughout the history might have affected the grain size of the swords. A Japanese metallurgist named Masahiro Kitada once conducted a study on crystal grain of 30 different katanas dating from Kamakura to Edo period. He found that among 30 randomly corrected swords, those made from Edo period has larger crystal grain size compared to the one made in earlier period. The difference was especially noticeable in the grain size near the blade edge, with Kamakura period swords having a grain size of around 1 to 5 micrometers, while Edo period swords have grain size of around 20 to 30 micrometers. That's a big difference. It means that the swords from Kamakura period, which are analyzed in this study, are harder in high possibility, and when the crystal grains are smaller, which can lead to differences in the texture and color, even if the material is the same. I think it is possible that sword making techniques, such as heating techniques, changed over time. Differences in the size of the crystal grains emerged, which could have contributed to spread the rumors about superior swords from certain periods. But please note the following. The difference in crystal grain size across different periods is only a possibility, and the truths are unclear. This is because only 30 swords is examined, and they may be biased. The discussions about crystal grains I presented here is just only one way to strengthen steel. There are different principles at play, such as the structure of the crystal themselves and solid solution strengthening that can also make steel stronger. I'd like to create a video about those topics as well.